Right. So yesterday we started with the topic of Newton's laws of motion. So we'll continue with that today. Yes, syllabus of upcoming test, Aparna, will be the kinematics portion only that we have discussed. Newton's laws will not be included because we have just started it this week. Okay. But you will also have that small part of two-dimensional motion, which involved vector analysis that we discussed last time. So everything that we've discussed till the last lecture before this, the one, before yesterday's lecture. Yesterday's lecture, we started Newton's laws of motion. So before that, we were discussing kinematics and circular motion also. Yes, Adinath, correct. So basically everything that is there in the first chapter of your physics 1. Now, of the module physics 1, the first chapter has kinematics, motion along a straight line, little bit of vectors, introduction to vectors, and circular motion concept. So that is the portion for your upcoming test on Sunday, people. Right? Okay, so now coming back to Newton's laws of motion. So we'll just take a quick recap of some things that we discussed yesterday with a couple of more examples. So we saw the laws of motion. So we saw the first law was basically about the law of inertia. So we had understood about inertia of rest. And that basically has to do with mass of the body. We also saw about the inertia of motion. And that has to do with the quantity of momentum. So the more the momentum of a given body, the more the amount of inertia of motion it has. Whereas if a body is at rest, the inertia is represented by the mass, or you can say it is proportional to the mass. Now let us understand the inertia of motion concept with another example. So we have an example wherein, let us say, you have something like a billiards ball or a snooker ball moving on a snooker table with a certain velocity v0 or with a velocity v. Now what happens here is, suppose we need not use vector notation, but you understand that velocity is a vector. Now suppose while it is moving like this, at some stage of its motion, it gets hit by something like this. It gets hit in a diagonal sort of direction like this. So today we'll also discuss about the concept of impulse, and this will become more clear. But let us say it gets hit by a force F like this, which acts for a very short amount of time, delta t. So this is like an impact force, like the type of force that acts in a collision. So here the quantity F delta t is the impulse due to a force F acting during a collision or an impact for a duration of time delta t. So delta t is typically a very short duration of time. So here what is happening is, you can see that in this particular example, the way I've drawn it, you can see that the initial momentum, let us say P1, which is mu. Okay, so let me make a correction and make this symbol as u. So the initial momentum and the collision impulse F delta t, okay, are not along the same line. you can see that the initial momentum is acting, it's a vector acting along this direction, the direction as such. We have previously understood that vectors have direction and magnitude. So its direction is along this arrow and its magnitude is mass into velocity. And then as it is getting hit, the impulse or the force multiplied by time for which the collision is acting, that is acting along this line. That is acting along this line over here. So that line is not the same as the line of the initial momentum. So when this happens, so whenever this kind of a situation happens, that the force and the initial moment are not along the same line. Okay. So what happens is that the direction of motion changes. Okay. So therefore, the effect of the force F, or you can say the impulse F delta T, will be to change the direction of the motion. So as a result of this, what will happen is, this ball was coming in with a velocity like this along this line. Then as it came somewhere here, let's say after some time, it got hit by this impulse or hit by a force which acted for that very short time, delta T, like this. So after that, what we might observe is that the ball starts moving now like this. As a result of this impulse, the ball will start now moving in the direction perpendicular. So the final velocity of the ball might change, will definitely change direction as a result of this. See that like this. That is the initial. You can see as a result of the direction of the impulse being in a different direction or not along the same line as the initial momentum, you can see that mv, that is the final momentum, has a different direction compared to the initial momentum, which was mv. It's along a different direction compared to the initial momentum. So this example also displays the property of inertia. I'll give you time to note this down. So what is happening here is, this is also a demonstration of inertia of motion. That is, to change the uniform motion, that is P1 equal to mv, and by change I mean change in direction. An external impulse or force is needed, and the body in uniform motion tends to oppose this change. So that is the property of inertia of motion. So in other words, when we apply external force on a body which is already in motion with a certain momentum, it may not only change the magnitude, it can also change the direction of motion. So this is another example of the property of inertia of motion from what we were discussing yesterday. So these 2 points were noted down yesterday. Now just Additionally, note down this example. This is another example of the application of the concept of inertia. So just make a note of this, people. Okay, so for example, if this was a ball moving on a table like this, and there was some surface like a wall over here. So as it comes in contact with that surface, it will experience an impulse or a force in this sort of direction. As a result of that impulse of force, its direction of motion will change. So ये जो impulse लग रहा है, that's along a line which is different from the line of the initial momentum. So the result of this impulse will be that it will change the direction of its momentum. Okay, so finish writing this down. Yes, Yuvraj. Okay, good. Okay, so I guess all of you finished writing then. Okay. Now, next thing we saw Newton's second law. Okay, good. Okay, so we understood Newton's second law as the force law. It said that the net force acting on a body equals to the rate of change of momentum. And we also saw that if this law is applied to a body of constant mass, basically a rigid body, then we can say that delta P by delta T becomes M delta V by delta T. It becomes mass into acceleration. So then we can say that the net force equals to the mass into acceleration. But only in that case. This is a conditional state. This is when mass is constant. Whereas we also saw the example of the conveyor belt. If mass is variable, on the other hand, but velocity is constant, then we can write delta P by delta T as rate of change of mass with respect to time into velocity. In that case, this net force becomes delta M by delta T, that is rate of change of mass with respect to time into velocity. Okay, but this is for that special case when you have a variable mass system moving at constant velocity. Now today let us see an example. Mass and velocity. Yeah, Bhaumik, you have seen the force law yesterday. No? It is the same thing. So I'm just giving a recap. The force law you already seen yesterday. You need not write down on this again. I'll just give you a minute to go through this, but you don't need to write down all of this again. You've already written down all of these things yesterday. I'm just giving you a quick reminder of what we discussed so that you have that continuity. You remember these things while we are applying today. So this example we had seen of the conveyor belt. The conveyor belt example that we saw yesterday. That kind of. Now today, let's continue ahead and let's understand something where mass and velocity may both be variable. Both of them might be variable. So in that case, what do we do? Okay. For example, already I have the example. So suppose we have a situation where you have one of those standard tanker kind of situations. Now this is moving along such that water is leaking out. There is a leakage. So let us say that at some initial time, t equal to 0, it has a mass at this point of time. The total mass, the tanker plus the water, everything included, is equal to, let us say, 10,000 kilograms, about 10 tons, and is moving with a velocity u of 20 meters per second. Now, water leaks at the rate of 2 kilograms per second, and the tanker also accelerates at t equal to 0.4 meters per second. So first of all, find the momentum of the tanker at t equal to 0 and at t equal to 5 seconds. Then second, calculate the average force F equal to delta P by delta T on the tanker from t equal to 0 to t equal to 5 seconds. Calculate this. Okay, so just try this question out now. Just try to follow the language of the question and come to the solution yourself. You just follow the language of the question. Just try out the first part, then I'll show you the second part. Bhaumik, what are the momenta at t equal to 0 and t equal to 5 seconds? First, tell me how much the momenta are. Yes, Adinath, that is correct. So the momentum has changed, no? So the momentum should have increased actually. So if the momentum is increased, that means there is some change in momentum. No? So there will be some average force. So you get the average force very close to 2000 newtons. Oh, sorry, very close to 200 newtons. And you get it as 197.8 or something like that. Okay, so let's understand this. So what is happening is the first part's answers at t equal to 0, the mass m is 10 tons or 10,000 kg, and the velocity is 20 meters per second. Therefore, the momentum, let's say P1, is 20 into 10,000. So 200,000 or 2 lakh kg meter per second. Now we can just write this as 2 into 10 raised power 5 kg meter per second. So that's 1 kg meter, right? Whereas at t equal to 5 seconds, what is the mass? The mass will be the initial mass, let's say this was m0, minus some amount of mass which has been removed. So what is the amount of mass which has been removed? It is equal to the mass which is leaking out at the rate of, water is leaking at the rate of 2 kgs per second. So 2 kgs per second multiplied by 5 seconds. So 10 kg of water is leaked out. So the mass is becoming 10,000 minus 10. So 9,990. Or 9.99 into 10 raised per t. And what about the velocity at t equal to 5 seconds? U plus 80. So that will be, initial velocity was 20 meters per second. The acceleration was 0.4 and the time we are taking is 5 seconds. So 22 meters per second. So the mass is this much and the velocity is this much. So the momentum, let's say P2, is the new mass into the new velocity. So 9.99 into 10 raised power 3 multiplied by 22 meters per second. Okay. So this will give you a momentum of this is the answer to the first part of the question. This is the momentum at t equal to 5 seconds, whereas the earlier value was the momentum at t equal to 0 seconds. You can see that the momentum has increased. So there is some change in momentum. So there must be some average force there. Okay, so now we use that definition to find the average force. Change in momentum upon change in time. Understood? So the second part of the question is now the calculation of average force. The second part we just use that the average force, average net force, will become change in momentum upon change in time in delta t equal to 5 seconds, or from 0 to 5 seconds. So the change in momentum delta p will be p2 minus p1, and the change in time will be 5 seconds. So p2 minus p1 you can see is 1978 kilogram meter per second, and 5 seconds. This becomes the answer. Sorry, it's close to 4,000, not. So that becomes the answer of the second part. Is the method clear, people? Yes, understood the question, everyone? Okay, very good. So now we will go on to a couple of more definitions before we come to Newton's third law. So within applications of Newton's second law, understand one more thing. First of all, we'll understand the concept of impulse due to a force. So the term impulse is the symbol that we use for impulse is J. Impulse is given by the symbol J, and it is defined as F delta T. So this is impulse due to a force F acting for a time delta T. So the impulse is just defined as force multiplied by time for which the force acts. The duration or the time for which the force acts. So therefore, impulse is expressed in Newton seconds in SI unit. So in SI system, it is expressed in Newton seconds. In CGS system, it is expressed in SI unit system. Or dyne second in CGS system. So just make a note of this definition first. This is part of the applications of the concept of Newton's second law. Just make a note of the definition and the unit. No, it's not tau beta. This is J. Okay, the symbol is capital J. J for July, that symbol. Okay, that tau symbol is this. This like this. This is tau. This is different. This symbol will be used for torque. You are correct. Okay. So my handwriting might have misled you, but this symbol used is capital J. Okay, now one additional thing you can see here. So finish writing down the definition. So another thing you can note down here is 1 Newton second is the same thing as 1 kilogram meter per second. In other words, impulse has the same unit as momentum. Impulse and momentum have the same unit, and they have a relationship also, which we will discuss next. Okay, this is easy to understand that 1 Newton second is equal to 1 kg meter per second, because you've seen the definition of 1 Newton yesterday. 1 Newton is 1 kilogram meter per second square. So multiplied by 1 second, it just becomes 1 kg meter per second, which is nothing but the unit of momentum. So impulse and momentum have the same unit. J is impulse, beta. J is Bhomik, J is the symbol used for impulse. Okay. This is the impulse, and this is momentum. E is think of it as it clear, Bhomik? J for July. That is, I was explaining. Yeah, Bhomik, I was just explaining that is that J, okay, and not tau. Don't worry about this. Yeah, it's okay, Bhomik. Doesn't matter. Is it okay? Is it clear now? Okay. Okay, done with this. Good. Now next we'll see something very interesting based on this definition of impulse. Okay. We'll see something called the relationship between impulse and momentum as an application of Newton's second law that we are saying. Okay. So the statement of second law is that net force is equal to change in momentum upon change in time, the rate of change of momentum with respect to time. So in other words, therefore we can say that delta P is equal to net force multiplied by the time interval delta, or delta P is equal to what we can say is the net impulse, where G net is the net impulse acting on a body in time delta T. And as a formula, that net impulse will therefore be given by the net force multiplied by the time. Now, force into time is impulse. So net force into time becomes net impulse, like that. So G net is equal to F net into delta T. And on this side of the equation, delta P equals the change in momentum in time delta t. During time delta t, whatever change in momentum. So this is called the impulse momentum relation, that the net impulse equals the change in momentum. In words, this statement becomes like this. So this is a direct application or a direct result of the statement of Newton's second law. If we just cross multiply the delta t over here, you can say that the net impulse or net force multiplied by time delta t is becoming the change in momentum during that time. Okay, very good. So now we can see some numerical applications based on this concept. All of you understood this so far, I hope. Yes. So next example. Understand like this, that we have a smooth surface and a ball is rolling along the surface. The velocity let's say it is 1.5 kilograms, and the speed with which it's moving initially, that is equal to, let us say, 2 meters per second. Now the ball hits the wall and rebounds at 1 meter per second. So find the impulse applied by the wall on the ball, and second, the loss in kinetic energy due to the impact. During the impact, what is the loss in kinetic energy? So just take down the question first. I'll explain this question, then we'll do a couple of more questions. Yes, Aparna, very good, that's correct. No, wait, Aparna, check your first solution, okay? Remember that momentum is a vector, so it has direction. So there's algebraic sign involved. Just check your first answer, Aparna, the first part's answer. Okay, so this is the initial state of the ball. Yes, Dhruv, that's correct. नहीं बेटा, change in momentum निकालेंगे ना, final minus initial अपन ना. So what you given is correct. That's the final momentum. Okay, this is the initial state. नहीं Adinath, okay, I'll explain. Okay, now during impact, what is happening? Okay, this is during the collision with the wall. The ball is experiencing ultimately an impulse like this. It's in contact for some time, so it's experiencing an impulse, the horizontal direction like this, let's say. So that impulse is some amount of force acting for a very short duration of time, delta t. And as a result of that, now what is happening? The ball finally is moving like this. It's having a velocity in the opposite direction. So the final state of motion of the ball is now like this. It's like this. So this is the final state. Okay. So if I take this direction as my positive x-axis, okay, so what I'll say is that my initial momentum of the ball is how much? It is plus mu. So it is positive of 1.5 kg into 2 meters per second. So it is positive of 3 kg meter per second. Okay. But what about my final momentum? Remember, momentum is a vector quantity, it has direction. So if it's in the opposite direction, we have to give with algebraic sign, na? Minus mv. So it is how much now? It is minus of 1.5 multiplied by 1 meter per second. It rebounds at 1 meter per second. Okay? So minus of 1.5 kg meter per second. मेरा final momentum इतना है. So what is the change in momentum? Delta P is equal to final minus initial. So it is minus 1.5 minus of plus 3. So it is minus 4.5 kg meter per second. And the minus sign is just showing you the direction. So you can see that an impulse g equal to 4.5 kg meter per second along the negative x-axis acts on the ball on impact. Okay, so this is the proper answer to the first part. And that's why the answer to it is 4.5 in magnitude and direction, of course, backwards. Okay, so this is the solution of the first part. And the second part is simple. It's kinetic energy is a scalar quantity. So initial kinetic energy is half mu square. Final kinetic energy is half mv square. So the change in kinetic energy is half mv square minus u square. So that is half of 1.5 into 1 square minus 2 square. So that is okay, 3. So 3 by 2 is 1.5. So 2.25, but with a minus sign. So the change in kinetic energy is minus 2.25. Okay. Joules. This is a change in kinetic energy. So therefore we can say that the loss in kinetic energy is equal to 2.25 joules. There's a 2.25 joule loss in kinetic energy. Okay. So hope this is clear to all of you people. Just note down the first part of the solution first, then I'll come to the second part. Okay, so hope it is clear to all of you that the impulse will have a magnitude of 4.5 Newton and not 1.5 Newton. Yes, very good, Beta. So that's why you have to be careful with the vector quantities. Okay, whereas kinetic energy, any type of energy for that matter, work done and energy are scalar quantities we discussed, remember. So there's no directionality involved. The final and initial kinetic energy, they just depend on the mass and the speed. They don't depend on the direction of the velocity. Okay, good. Okay, so now let's do a trickier version of this question where you will, so hope you've written down all of you, okay, where you'll have to involve a little bit of your equations of motion that we discussed last time, okay, the last few lectures. So next example, something like this is happening. Somebody drops a tennis ball of mass, let us say 250 grams, is dropped, okay, from this height of, let us say, 20 meters, okay, and it rebounds from the ground below, and you take acceleration due to gravity as 10 meters per second square. Now it is observed that after the first bounce, the ball climbs to a maximum height of, let us say, 15 meters. It climbs to a maximum height of 15 meters. Okay. So calculate the impulse on the ball on impact with the ground. Okay. So just try out this question. Use the value of g to be 10 meters per second square in this. Right, solve it. So sorry, Gomik. Just try out this question, Gomik. You can write down the other one later. Just try this question. Okay, people got the answer? Yes, Aparna, I think what you got is correct. Let me just check. So we have to solve this problem actually in three parts. Now we have to understand what is the impact velocity. So the first thing we have to understand is that you drop the body, you dropped it from a height of, the initial position is at a height of 20 meters, right? So when it hits the floor, just about to hit the floor, you can say, when that happens, its velocity at that point of time. First thing is we have to calculate that velocity. So if this is v1, okay, the velocity just before impact. So because it is starting from rest, from a height of h, and the acceleration is g downwards, so velocity just before impact, that will be how much? Root 2 gh. Use the relation that v1 square is u square plus 2gh, from the relation that v square is equal to u square plus 2as from this one. So we'll get v1 as 20 meters per second because this h was 20 meters. Okay. G was 10 meters per second square. This is the first thing. Okay, now we also need to find out that what is the velocity just after impact. Because okay, now once the ball is hitting the floor, during that impact, it will experience an upward impulse, G equal to F delta T. But as a result of that upward impulse, now what's happening? Its velocity is changing to something like this. Its velocity is changing to some V2, let's say, in the upward direction. So just after impact, if it has a velocity V2, this is just after impact, the velocity is V2. Then now the maximum height to which it is going, where its velocity will then become 0, is some height h prime, which was 15 meters, let's say. It rebounded to 15 meters. So V2 square should be equal to 2g h prime this time. Because this time we'll take 0 square is equal to V2 square minus 2gs, and s will be equal to h prime. Okay. So my V2 will become square root of 2 into 10 into 15. Okay. So V2 will be 10 root 3, or approximately 17.32 meters per second upwards. Whereas my V1, remember, was this downwards. Okay. So now we will apply the impulse momentum theorem. So we understood this thing. Before impact, during impact, and after impact. So impulse is equal to change in momentum. Okay, delta P, the impulse. So J should be equal to final momentum minus initial momentum. So final momentum is plus of mv2. Initial momentum is minus of mv1 because this was downwards, this was upwards. So it is m into v2 plus v1 हो जाएगा. So m is 250 grams into 10 root 3 plus 20. So that's 1/4 of a kg multiplied by 17.32 plus 20. So that is 37.32 by 4 kilogram. This is in meters per second on this. Meters per second. So the impulse is approximately 9.33 kilogram meter per second or Newton second, whatever unit we choose to express. This is the impulse. Applied by the ground. Okay, so hope this solution is clear to all of you. Just minimizing this a little more so you can understand in detail. I had taken the mass to be 250 grams only. Let me just recheck. Yeah, 250 grams dropped from a height of 20 meters, and after impact it went to a height of 15 meters again. So velocity changed from downward v1 to upward v2. So momentum changed from a negative value to a positive value. So change in momentum is final momentum, which is positive, minus of initial momentum, which is negative. So minus minus will again become plus. So that's how we're getting the collision impulse as this. You just note down this properly. Grams is this thing, but a unit of mass. Anshul, 1 gram is 1,000th of a kilogram, no? Or 1 kilogram is 1,000 grams. 1,000 grams. This is grams. This is the CGS unit of mass. Yeah, Bhaumik, the last part, we are just calculating the change in momentum. Right? Impulse is equal to change in momentum. So final momentum minus initial momentum. So final momentum kya hai? The final momentum is mass into this velocity, that is 250 grams into 17.32 meter per second, but upwards. Whereas the initial momentum, why we are writing it as minus mv1? The minus sign is showing that it is downwards. Okay, so that is why the change in momentum is becoming minus minus plus. So the unit is grams into meter per second. So 250 grams are converted to kg. So I've solved it till the end, na beta. I've calculated in SI unit, na. 250 grams is equivalent to 250 upon 1000 kg. Or that is the same thing as 1/4 of a kg. Okay, no? That's why I've converted it. So here I've converted it to SI unit. This was in gram meter per second. I've converted to kg meter per second, which is the SI unit. Okay, is it clear now, Bhaumik beta? So change in momentum, it becomes mv2 minus minus, so plus mv1. I've taken the mass common. Okay, so now the mass is 250 grams and v1 and v2 are both in meter per second. So now 250 grams को convert किया है. So that is a separate thing. 250 grams is the same thing as 1/4 of a kg. That is the conversion I have used. Alright, so this is clear, but I hope. Okay, good. Okay, so hope this example is clear to everyone. Okay, now we'll move on to Newton's third law, the final of the three laws. Okay. The third one, the action-reaction principle. Okay, okay. Okay, Yuvraj will do like that. When we finish Newton's laws, we will keep we'll keep some problem solving sessions for Newton's laws, and in that we will include one problem solving session for relative motion questions also from the booklet and all. So action reaction principle, the statement says that every action has an equal and opposite reaction. Okay, so this is the one that we are all used to experimenting a lot with. We tend to slap each other and see that okay, our hand is paining with the same amount of pain that the person we have slapped's face might be paining or something like that. So we all tend to do experiments to prove this particular principle and gives us an excuse to hit each other and all that. But all that jokes apart, okay, it's a very important principle which comes from the very fundamental nature of force. So let's understand some examples to get this. So before that, let's also understand the statement in a more clear way. Okay. So what does this equal and opposite reaction actually mean? So it implies that if a body, let's say E, applies some force on another body B, then B will apply an equal and opposite force minus F on P. That is the meaning of action and reaction. If one body is applying an action on the other one, the other body will apply an equal and opposite reaction on that. So it will apply an equal and opposite force. So opposite matlab minus ho gaya, opposite in direction minus F, but on which one? On E. So this force that E is applying on B, if that is the action, then this one becomes a reaction. So in a diagram we can understand like this, that suppose we have a situation where you have a person and you have a box. Now suppose the person pushes the box with a force F, suppose. Then the box will push the person back with an equal and opposite force minus F. That is the principle. So this is the force on the box, okay, applied by the person. We are calling this the action. Then this is an equal and opposite force on the person applied by the box. This will be the reaction. Okay. And they will be equal and opposite. Equal in magnitude, but opposite in direction. So this is the proper illustration of Newton's third law. That if A is applying a force on B, then B will apply an equal and opposite force on A. Or if a person applies a force on an object, the object will apply an equal and opposite force on the person. Yeah, this is only the formula, na, that F and minus F. The force applied on B due to A is minus of the force applied on A. So this is the force on B due to A. It's equal and opposite to the force on A due to B or applied by B. So moving more importantly, we'll see there are applications of this concept of action and reaction. Okay, this is done. Another example of this is, for example, you have electrostatic force. It could be in the form of repulsion between what we call like charges, like two protons, they repel each other, or it could be attraction between opposite charges, okay, like a proton and an electron attract each other. But these forces also show themselves in the form of action-reaction pairs. Suppose we have a positively charged body and a negatively charged body. Okay. So they will attract each other, but they will attract each other in such a way that the force that with which one attracts the other is equal and opposite to the force with which the other attracts the first. This and this forces will be like this. So if we have charged particles A and B, suppose, attract each other. Okay. Now that happens such that the force that B applies on A will be equal and opposite to the force that A applies on B. So this should be EB. Here also we'll see that the force that B applies on A will be negative of the force that A applies on B. Okay, so the attractive force on A due to B, that is equal and opposite to the attraction force on B due to B. So this is the action. It is equal and opposite to the reaction. That's another example of action-reaction force. Okay. So now let us understand some more examples based on this. So block A is placed on B which in turn is placed on a smooth horizontal surface. Now, given that mass of A is 2 kilograms and mass of B is 8 kilograms. So what we want to do is now we want to find the contact force, or what we also call the normal reaction force applied by E on B in newtons with direction indicated. Then again, the contact force applied by the ground on B, again in newtons with the direction indicated. So just try out this concept, this question here. So you have to just understand the concept of action-reaction principle. Okay, once you apply that over here, you will understand how to solve each of these parts. The word normal in geometry means what? Perpendicular. So normal reaction का मतलब क्या होता है? Perpendicular to the surface. So whenever a body lies on a surface, there is a perpendicular component of force because of the contact that acts. Right, that is correct. Aparna, your answer is correct. Yes, Adinath, it's correct. Bhagyashri is correct. No, Bhavin, check your answer. Okay. So see, here what you have to understand is, if this is the block A, suppose, separately, we just trying to understand the forces acting on it. This is the block B, and this is the floor below. So block A ko ground will be pulling it down with a force equal to its weight. This is nothing but A's weight, which is nothing but the gravitational force on A applied by the ground. So what will be the direction of contact force applied by the second body on A? It will be upwards. The second body, B, will be applying a normal reaction on A, which is upwards like this. Applied by B. Just a second. Just give me a moment. The screen will come back on. So this is the normal reaction applied by B on P. Because A is in equilibrium, what should happen? This normal reaction has to balance its weight. So it has to become equal to 20 newtons. Now when you look at the body B, its situation is somewhat different. For the body B, what is happening is that E will be applying a downward force on B, which will be like this. This will be the same magnitude as that one. So this is the normal reaction on the block B applied by E. So its direction is opposite. So you can see this one and this one are an action-reaction pair, but its magnitude will be the same as this, 20 newtons. Okay. Whereas of course B has its own weight. So ground is pulling it down with a weight. Okay. And of course the floor will be applying an upward normal reaction on B, which will be like this now. This is the normal reaction on the block B applied by the flow. So you can see that as far as block B is concerned now, the net force on it has to be 0. So for block B, the downward force that A is pressing it with plus the weight of B, that is the total force with which is pressing on the floor below. So the floor will react by applying a normal reaction upwards. It's like on the floor now, B is pressing with a force like this. So the floor is pressing back B upwards with a force like this. Okay. So this will become 20 newtons plus 80 newtons. So this will become 100 newtons. Okay. So before you write this down, just want to illustrate this point again. So A is lying on B and B is lying on the floor. So क्या हो रहा है? B A पे एक upward normal reaction लगा रहा है and A B पे एक नीचे की तरफ normal reaction लगा रहा है. And similarly, B is pressing the floor down with some normal reaction, and the floor is pressing it back up with some normal reaction. Okay. So that is why when you see the block B, on its two surfaces there are two pressing forces. ऊपर से A is pushing it down, नीचे से the floor is pushing it up, and of course it has its own weight. This is the block B. Whereas the block A you see, then नीचे से the floor, I mean B is pushing it up with a normal reaction like this, and of course it has its own weight, which is like this. So these are the action-reaction pairs. So this and this are an action-reaction pair. This and this, they're an action-reaction pair. Similarly, these two are an action-reaction pair. The floor pushes B upwards and the B pushes the floor downwards. The block B pushes the floor downwards. So those two forces are an action-reaction pair. Similarly for the other two. Alright, so this is the complete description of this. So just make a note of this part. Okay, good. So we will hope you understood this question fully. The two answers are like this. So, to answer this question properly, the contact force, normal reaction force applied by A on B, that will be equal to 20 newtons downwards. A will be pushing B down like this. This normal reaction will be 20 newtons in magnitude. Okay. And similarly, the contact force applied by the ground on B. Okay. So that will be how much? That force will now be 100 newtons upwards. So on B, the ground is applying a force of 100 newton upwards. So this is happening because of this concept of action and reaction. So let's understand through this diagram again. See क्या हो रहा है? The block A is pulled down by gravity with its weight of 20 newtons. This is the gravitational force on it. So as a result of that, it presses against the floor. I mean, it presses against B. So as a result of this, A is pressing against B because A is lying on top of B. So it's pressing against B with a normal reaction force in it. And B is pressing back A with an upward normal reaction force. Like this. So because this block is in equilibrium now, it's at rest. So this normal reaction with which B is pushing A upwards, that has to balance the gravitational force with which it's coming down. So this has to be 20 newtons. So if this normal reaction is 20 newtons, then that means this one here also has to be 20 newtons. Okay. Now in addition to that, B को earth pull कर रहा है, gravitational force of earth on B, that is equal to how much? 80 newtons. So this force together with the gravitational pull of the earth is pressing B against the floor. So the floor has to react back by applying an upward normal reaction on B. And that has to do what? That has to balance the sum of these two. So it has to be 20 plus 80. So it has to be 100 newtons. Okay. So that is why this force here, this is going to be 100 newtons. Whereas this force here, this is going to be 20 newtons. Is it clear now, Bhaumik? Understood this better? Yeah, there's nothing else better. This is all I've written now. इतना ही है. Okay, done. Okay, let's look at another example to understand this. So now suppose I have this situation. There are two blocks which are kept against each other. on a frictionless surface. So this is a smooth horizontal surface. Now this is the block E, which is having a mass of 40 kilograms. This is the block B, which is having a mass of 10 kilograms. Okay. And now there's a person who's pushing the system like this so that it accelerates like this. So the person pushes against E towards the right hand side with a horizontal force of 100 newtons. Okay. So he's pushing like this in this direction with a horizontal force of 100 newtons. So now you have to find, as a result of this, the force, like normal reaction, with which the block E pushes B. The force with which B pushes E and block in these accelerations. So this is what we have to calculate in this question. So these two you have to give in newtons. And this one you have to give in meters per seconds. Okay, so very similar to the previous question, you have to just understand how the two bodies A and B are interacting with each other. If A is applying some kind of action on B, B will apply an equal and opposite reaction on E. So just understanding that concept and applying Newton's second law, you will get the relationship that I'm telling you to try. Anybody got the answer yet? No, beta, 100 newtons is not the correct answer. Okay. So let's try and understand what happens here. See, suppose this is the block A. Now you are pushing it from this side with the force of 100 newtons. So what will happen? This will push against B. So actually there is no gap between them, but I'm just showing like that. So as a result of the force that you are applying, this one will push against B with some normal reaction force, let's say N. वो force कितना है मुझे पता नहीं, but suppose it's some, but its direction will be like this. So this will push back with the force of N. So this is an action-reaction pair. This is the force, the normal reaction on E by B, and this one is normal reaction on B by E. So they are equal and opposite. Okay, so they are an action-reaction pair. Okay. Now, as you're pushing this system, the whole thing will slide together with some acceleration. So जितना इसका acceleration होगा, इतना ही इसका भी acceleration होगा. Okay. So now you can see that for block E, what is happening is the net force should be equal to mass into acceleration. So net force कितना हो जाएगा? F minus N, and that is this one's mass into acceleration. Whereas for block B, the net force is how much? It is only N. So it will be B's mass multiplied by acceleration. So equation 1 and equation 2. So equation 1 will tell us that 100 minus N is equal to 40 E. And equation 2 will tell you that N is equal to 10 E. Okay. So now add the two equations and you get the value of acceleration. Or subtract the two equations and you get, okay, so like this. So from equation 2, you can substitute E as N by 10. So substitute this in equation 1. So you get 100 minus N is equal to 40 E, which is N by 10 or 4N. You want 100 minus N is equal to 4N, or 100 is equal to 5N, or this normal reaction is equal to how much? 20 newtons. That's one. So therefore, E applies N equal to 20 newtons to the right on B. Okay. And B applies N equal to 20 newtons towards left on B. So while they are moving, E is applying on B a force like this. B is applying back on A. You are applying a force of 100 newtons. As a result of this, A and B are both having the common acceleration. both E and B move together with a common acceleration of 2 meters per second square. So that becomes the proper answer or the complete solution of this. You understanding, people? So जो force आप 100 Newton का लगा रहे हो ना on E, that is not directly acting on B. That you are applying on A. But A is applying a lesser force of only 20 Newtons on B. And B is applying back an equal and opposite force of 20 Newtons on E. So A पे देखो अभी क्या हो रहा है? Net force कितना हो जा रहा है? F minus M. This is 100 Newtons. This is 20 Newtons. Okay, so you can see 100 minus 20 is equal to the mass of A, which was 40 kg, into the acceleration, which was coming out to be 2 meters per second square. You can see left hand side is equal to right hand side. Whereas on B, what is happening? There is only a force of N equal to 20 Newtons acting, and that is creating an acceleration of 2 meters per second square. So N is equal to mass of B into acceleration. So 20 Newtons is equal to mass of B, which was 10 into 2. So it's again LHS is equal to RHS. So this verifies that what we have calculated is correct. So again, you can see the action reaction principle in play over here. That the blocks A and B, they apply equal and opposite action on reaction on each other. Okay, that is the concept of Newton's third law, that every action has an equal and opposite reaction. Yes, I'll scroll down. Just wait a minute for people to note down the first two equations, then I'll scroll down and solve. Ishan, module 2 will be much later after we finish module 1. Module 2 को time है बेटा अभी. No, beta, projectile motion will not be coming in this test. Okay. I'll just give you a list of the things which will be coming in this test. Okay, so we're almost done. We'll just conclude with this. these are the things that you cover for the test. Okay, students, so wish you all the best for the test coming up on Sunday. Please do a revision of these things, and especially the questions that we solved from the module in class in the last 3 or 4 lectures that we had solved. Okay. Yeah, relative motion is also part of the straight line, but only in straight line. Okay, so including examples of relative motion, but only along a straight line, not in 2 dimensions. So that is part of motion along a straight line. Okay, including. Okay, people. So that's it for today. Wish you all the best. Okay, and please do some revision before the test. And if any doubts and things come up, you can message me directly. I'll help you.